Hey team, welcome. Today we're going to be talking about capacitors and RC circuits, RC standing for resistance capacitance. I wanted to highlight first capacitors because I saw there was a little bit of confusion. So let's get into it. So a capacitor is a device that can hold electric charge and electric energy. And the way that it does this is that we have a battery source, and using the current, which is a stream of charged particles traveling through an electrical conductor or space, in this case the wire, we have a direction, let's say here, where our current is going in this direction, and we have a positive charge on this plate. Now, the other side, the negative side, right here, we have a negative charge. Now, the reason why we have this, and I'm going to try to make it brief, is because in actuality, remember, the direction of current is just a convention. What's actually happening is the movement of electrons. So when we put a battery on and we see a plate here, what's happening is that electrons are moving away from the plate, and it's positively charging the plate because there's less negative charge in that plate. In this side, in this plate right here, we have the battery moving electrons into the plate, and that's why it is negatively charged. Now, another thing that happens is that current starts decreasing because there comes a point where the capacitor meets its maximum charge. And because it meets its maximum charge, there's no longer any way to put more charge into these plates. It is in complete equilibrium, whereas this charge, this plate right here, has the same positive charge as this plate right here that I'm highlighting right here that has the negative charge. It is in equilibrium, they're neutral. If we decide to take the battery off from the circuit, what happens is that it doesn't actually discharge. The charge stays in the capacitor. And the reason why is because it has nowhere to go. There has no route. Remember, closed circuits are when you're able to have the current go through the actual circuit. But if it's open, you won't be able to. That's why we still have a charge in the capacitor. Lastly, if we do connect these two ends, then we have a transfer of a charge going around the circuit. And different from graph A right here, or figure A right here, the current is actually going to travel this way. Because remember, current goes from positive to negative. So since there's a plate right here and there's distance right here, there's no actual charge actually traveling from this plate to this plate. They're going to take a different route. It's taking the route of the circuit all the way around back to this plate until the whole system is in equilibrium and the charge in the capacitor dissipates. Now, as I said before, current is a nomenclature, or not a nomenclature, a convention. What's actually happening is electrons that are moving. So once we connect it again, electrons will start moving from the negative side of the plate to the positive side of the plate. And that's how it starts going back to equilibrium. That's how it starts, the charge starts decreasing in the capacitor. And I say dissipate, but it's actually decreasing in the capacitor. And we'll talk about a little bit more about those in the graphs below. But I'll let's talk about series and parallel really fast. The most important thing is we need to know that when it comes to a series and we're looking at the equation that relates voltage, charge, and capacitance, that voltage is changing and charge is staying constant, because the same amount of charge being hit here, and let me put it in red, being transferred here is the same amount of negative charge being transferred to this plate. So these two plates are in complete equilibrium. Therefore, these two plates are also in equilibrium, because the same amount of positive charge has to be, negative charge has to be in the other side as in the positive charge. Okay, so this is the reason why we have constants. The charge is constant. But if we put electric potential, if we measure the electric potential from here, A, to B, then we would have a different electric potential from C to D, because it is a completely different capacitor. So electric potential changes as you go through the capacitor. So let's follow Kirchhoff's rules and do a loop. And we're doing a loop clockwise, and we are going to annotate that we're taking the battery, which is E, and I'm just going to write, V for, here we go, minus the charge in 1, or not the charge of the electric potential in 1, and minus the electric potential in 2. As I mentioned before, current goes from high to low. And when it comes to capacitors, it starts from high, the electric potential starts from high to low. If you have any other questions, follow the DC circuits video about understanding the differences in that. But because we analyze this, there's negative voltage coming from the capacitor, and all of that will find its equilibrium and find it equal to 0. If we change the equation to represent, since voltage is changing, Q over C, which is the capacitor of the entire system, minus Q over C1 minus Q over C2, you'll notice that since Q is constant, you can cancel these out, and the only thing left is this equation. Which, by the way, is the same equation that you have on your PRC right here. Okay? So that's how you do capacitors in a series. How you do capacitors in a parallel. This time around, following Kirchhoff's rules again, notice that we have a junction right here, and the way in which each current travels is split. Therefore, the way that charge travels through the conductor is also different. Thus, this Q1 is different from Q2. But if we would measure the electric potential here from A to B, it would still be the same electric potential as if we measured from C to D. And the electric potential doesn't change because Unlike the series where we have actual, basically, let's put it like this, like it's actual blockage of we have C1 first and then immediately after we have C2. In this case, it's both of them are in a parallel. It's not really affecting voltage, but it is affecting current. Thus, if we rewrite our equation as charge equals voltage times capacitor, and we follow Kirchhoff's rules, and the sum of the charge is equal to charge 1 plus charge 2, and we rewrite this as V, voltage constant, C as equivalence, C equivalence meaning C for the whole circuit, C1 plus C2, and then, and the voltage too, don't forget that, and we cancel these out. You have the same equation for conductors in a parallel. Okay, so I wanted to talk to you about that, which is great. Now let's move on to charging capacitors. So charging capacitors, I know that we had a little bit of struggle with this, and it's basically the meat and potatoes of RC circuits. So let's look at the examples from the book, and I took this diagram out. So let's first talk about charging capacitor. And the way that we start talking about charging capacitor is by moving the switch from being neutral to going to A. Okay, like it's showing right here. It's going to A, completely ignoring B. So current is traveling, it hits the resistance, and then it starts charging the capacitor. At this point, notice charge versus time capacitor, meaning this is the rate at which the capacitor is charging. Okay? If we do it in Kirchhoff's rules type, where we go counterclockwise, and we analyze what's actually going on in this circuit, we write EMF, electromotive force, which is also representative of a battery, minus the voltage going through the resistor, or not going through, across the resistor, minus the voltage across the capacitor, equals 0. We rewrite it again on terms that we know. And understanding that since charge is increasing, and as I mentioned before, that current is decreasing over time, it means that current is not constant in this term, but it has to do with the change in charge over the change in time. So we rewrite this as dq dt, which is equal to current over time. No, okay, it's actually current with respect to time. There we go. Not forgetting R. Minus QC equals 0. Okay. If we rearrange this, we are left with dq, the change in q, derivative of q, derivative of charge, equals EMF times the capacitor minus the charge, the capacitor, over RC, resistance capacitor, with respect to derivative of time. Now, if we have derivative here and we have a derivative here, then if we integrate this equation, we're able to get charge over time is equal to capacitor times EMF, electromotive force, in this case the battery, times 1 minus e to the negative t over RC. I remember one of you asked me where this RC comes from. It's this mathematical equation as we start changing the change in charge over the change in time, which is electric current. And this is how we get to that point. Okay? Now, RC is also can be rewritten as tau. And if we do a quick analysis on what RC stands for, so if we change R and using the equation right here, we have V over I, which is voltage over current, times charge over voltage, just like in this equation right here. Then we would come out canceling voltage on each side and then rearranging this. So now charge is coulombs, right? Charge is representative of the unit coulomb. And then current is representative of coulombs per second. This term right here turns into seconds because the coulombs cancel out and all you'll have left is seconds. So this is a time constant. What it's telling us is that if we go closer to this graph right here, if, let's say, we rewrite this, QT equals capacitance times EMF times 1 minus e to the negative RC over RC. And the reason why I do that is because I'm showing you that in this point right here, once we get to that constant in the charging of the capacitor, then at the bottom here, you see the time at here, it will be equivalent to RC at the bottom. They cancel out, and you will have left is 1 minus e to the negative 1. E to the negative 1 is, the value is 0.368. Now subtract 1 minus 0.368 and you'll get 6.632. It is saying that once we know the time constant for this circuit, we can find out what is the charge at 63% once it reaches the 63% of the charging. Okay? All right. So now let's go to this one. So in this one, you have to remember that as the charge of the capacitor increases, the current through the resistor decreases, as we were talking about before in our original diagram. In this case, I'm sorry to say, but you're going to have to do some derivatives. But it's not that bad. If we write down the equation for current over through time, with respect to time, equals change in current, change in charge over change in time, equals, again, we've changed the charge with the equation that we have right here that I'm highlighting right now. Let me erase this so we don't get confused. We can write down 1 minus e to the negative t over RC, or tau, and derive this equation. It results in this, that current with respect to time equals EMF, the charge or the voltage of the battery, over resistance times e to the negative time over RC, or tau. And this is your equation for current. I realize that they don't actually give you this in the PRC, so you're going to have to make sure that you understand how to derive, or at the very least, how to get to this point. The same goes with current in respect with the graph, right? So we have the graph right here. We go, okay, current, respect to time. And this gets to 1. E to the 1 is 0.368. And that's why we can figure out that once we know the time constant, we can find out the current once it hits the time constant right here. Okay? Well, let me talk to you about voltage versus capacitor over time. It is very simple. It's just like basically changing the equations. So if we look at our equations here, we have the two right here that are extremely important to manipulate this equation. We start off with the charge equation, and it's asking voltage versus the time capacitor, okay? If we just divide by C, by the capacitor, then this looks awfully familiar, right? Just rearranging this, and you will get voltage across the capacitor over time. Voila. Awesome, right? I know, it's super boring. Just keep up with me. This is just in case. Keep this in your tool bag, just in case. Like, how exactly do we get to this point? Well, this is how we get to this point, because Captain P has shown you the way, and I understand the classes are brutal, right? So, like, I just want you to pause, reflect, and then relook at the video. That's the type of thing. That's the reason why I do these kinds of videos. Okay, so in this one, voltage versus time resistor. In this case, we're looking at resistor. We'll use the same equation as this one. Current not means EMF over R. That's basically what it means. So don't get super confused by it. I'm gonna change this. Right here. Now, if we use the equation again for V equals IR, voltage equals current times resistance, we can rearrange this as we multiply on both sides for resistance, R, and this one right here, we multiply by R2, and we're left with voltage across the resistor over time equals EMF times e to the negative t over tau. Tau meaning RC. Okay? Alright. That is charging a capacitor. So we're going to go a little bit quicker with discharging of the capacitor. As we spoke before, when we start discharging and we move from being neutral to A now, to B now, then the capacitor, which was charged before, starts following, has a route now, and starts following through from positive to negative, and that is the current. And that's why we have this arrow right here facing that way. It's going, unlike when we initially started, which is going clockwise right here, this one is going counterclockwise because it is following the current. Follow the current from positive to negative, you'll never go wrong. Okay? In this situation, we no longer have a battery to be concerned for. So we just have to concern ourselves with the capacitor and the resistance. It still follows the same process as Kirchhoff's rules. So since current passing through a capacitor is minus voltage through across the capacitor, and then voltage across the resistor is minus voltage across the resistor. Okay, it's kind of redundant, I know. Equals 0. We change the wording or the equations, and this right here is the initial charge of the capacitor. Okay, plus I R equals 0. And I don't like skipping steps because you guys, I skip a step, it's completely detrimental to like what just happened. It's like, oh no, what happened? I am so confused. So I'm going step by step on this. I change I, and that's why we have dq over dt. Okay, following the equation again, minus initial charge of the capacitor over the capacitor. And we can integrate now, moving dt to the other side. And now we can integrate. And you realize that I'm skipping this. You can easily find this on your book. If we just go to chapter 10, RC circuits, and just putting it out there, like you do have a book. Oh, look, it's the equations. Okay, fantastic. Okay. So we get to this point and we write qt equals q naught for e to the negative t over tau. And I already went through how we get to this point. You notice the e to the negative 1. Okay. For getting the current, it is the same. You just have to derive and you'll get the answer. And I'm just writing it down for you to also write it down. Which equals minus q naught over rc e to the negative t over tau. I am gonna leave this part. I'm gonna leave this part to you. Okay, because if you understand the equations and just not playing around with them, but just be able to manipulate them correctly, you can come across with like the voltage across the capacitor and voltage across the resistor over time. Okay, so now let's go to a problem. And this is a part of one of your problems, and I decided to use this to help out understand, to give it actual context on a homework problem. This is a required problem, TP 10.93. Take your time, put it on pause, and read it. But our goal is right now 3 steps. We have to find the time constant. We have to find current right after time is 0, meaning that it closes, right after it closes, time is 0. So we need to find out what is the current there. And then finally, we need to find out what is the time when the current is half of its initial current when it started. Okay? So let's go for the first one. And it's asking us to find time constant. If we write the equation, which is right here in our PRC, and we write tau equals RC. And don't mind the C that's right there. A lot of people get confused with it. It's just constant, okay? Or for a capacitor. Either it's constant or capacitor, but don't worry too much about the C. Okay, so remember, when it comes to the resistant capacitor, is the resistance in capacitor across the whole system. So we have to find the resistance across the whole system, the capacitor across the whole system. For the resistance, it's a little bit more complicated than the capacitor. The capacitor only has one capacitor, but the resistors are 4 in total. So the way that we handle this is by understanding what our resistors are in parallel and what resistors are in series. Let's start off with understanding too that there are junctions here, junction A and junction B. Current here and current here are being split, or this current right here is being split into two. So we have a different current here and a different current there. If there are two different currents and there's a split, that is a hint that that is a parallel. But how much of a parallel is it? Because for this side right here, we have a resistor and another resistor in series. I specifically did this to show you, just in case, yes, it's not necessarily completely in a series, as you can, or like a straight line with squiggly lines, got it? But it is still considered a series. So R1 and R3 are still considered a series. This, since it has a different current, right here, it's its own entity, and these two sides are considered in parallel. Thus, if we do an analysis and we go, okay, well, let me just rewrite this as R13 equals R1 plus R3, right? Because it's in a series first. And then we go and jump R123 equals 1 over R13 plus 1 over R2, because now it's in a parallel, and that is to the inverse, -1. Okay, we have this. And now the only thing left, as I have here, is R4, which is also considered now, because now we're back, right? We're back here, and this part right here in current is the same current here as we started right here in this junction, okay? So if you want to do it like Kirchhoff's rule, we have I equals I plus 1, or I1 plus I2. And here we have I2, or I1 plus I2 equals I. So it's going all the way back to the same as we started from. Okay? So it is the same current, thus we also have the same, or we have a resistor in a series. So we go 1, 2, 3, 4, 5 equals R123 plus R4, and R1, 2, 3, 4, 4 1, 2, 3, 4, 5, no, 1, 2, 3, 4 is equal to R equivalence, which means the whole resistors from the whole circuit. With that, I'm not going to actually calculate the numbers, but I now can use my equation of tau constant equals resistors, the equivalent resistors, times Z, which is the only capacitor, and you get the time, the time constant. And that's it. Too simple. Now in this one, it's asking us to find the current right after the switch is closed. So we know that this is a charging capacitor. If we go back to our notes and we look at charging capacitor, we see right here our equation. I am just going to copy paste this equation. Hopefully it pulls through. I'll take it. And I'll just maneuver it. So I'll just put in this equation right here because it's the same one. And it's asking me, like, hey, what is the current at time 0? Well, I'll tell you what's the current at time 0. E to the 0 because it's time 0. Yeah, well, apparently current at time 0 is EMF over resistance. Too easy. Okay? And I have these graphs here just to show that, like, hey, as the capacitor is charging, remember that even though we start at 0, I mean the time of 0, and there's actual charge here, it slowly starts decreasing, or in this case it rapidly starts decreasing and then slows down as it continues going down to 0. And finally, the last part, and we're almost done. Oh my goodness, we're almost done. It's asking us, so what happens when initial charge is, well, we have to find the charge, not the charge, I'm sorry, I keep saying charge, the current, or the time when the current is halfway the initial current. Here we go. Oh my goodness, I struggle with that one. So in this case, we do know that there's a ratio. So I'll write the equation back down the way this one right here. And I'll write it back down. Okay. And now we just have to find out the actual, what the actual time. This right here, remember what I said? This right here means initial current. So if I bring this to the other side, this turns into 0.5, which is half, and I'm left with e to the negative t over RC. Then I do a natural log on both sides, and I have natural log of 0.5, remember, because we found the ratio, equals negative t over RC. Remember, the natural log, if you implement it on both sides, right, the e goes away, and what you're left is negative t over RC. Just in case, for those people that are struggling with mathematics, I get it. It's like, oh man, oh no, we're in trouble. No. Trust me, you'll be fine. Just continue on. And that equals t, which is time, minus RC times natural log over 1 over 2. And we are done. Obviously, I didn't actually give you the answer. I just did the algebraic solution because you know how it is. Physics loves algebraic solutions. I hope that this was fantastic for you. I hope that you followed through. If anything, just at least listen to me at 0.5 the actual speed that I'm actually saying, or 1.5 the actual speed that I'm actually talking. Okay? Anyway, this has been good. If you need other videos that are not RC circuit, any other classes that we give you, if you want me to focus a little bit more on capacitors and capacitance and dielectrics, or you want me to do a whole section on resistors only, write a comment below on the YouTube channel or in the actual video and let me know what you would like. Okay? Anyway, it's been a pleasure and have a good night.